Subscribe to the channel so you don't miss out on any of these videos. Imagine staring deep into the night sky, and within the vast ocean of stars, galaxies, and cosmic dust, there shines a beacon, a light so brilliant, so distant, that it challenges our understanding of physics itself. This light, more intense than any other known to us, doesn't come from an ordinary star or galaxy. Instead, it comes from an object we call a quasar. Quasars, short for quasi-stellar objects, are among the most radiant and enigmatic phenomena in the universe. Powered by supermassive black holes at the centers of ancient galaxies, these celestial beacons emit energy that rivals or even exceeds the output of entire galaxies. The study of quasars has not only pushed the limits of what we know about cosmic power but has also offered a unique window into the universe's distant past, unveiling secrets about the earliest epochs following the Big Bang. Quasars were first discovered in the early 1960s, a time when astronomers were piecing together clues about strange radio signals from deep space. Before the term quasar even existed, scientists had detected mysterious points of light that, though they appeared star-like, emitted radio waves and radiation far beyond what ordinary stars could produce. These points, initially just labeled as radio stars, captivated scientists, sparking intense curiosity and debate. What could produce such intense radiation from so far away? It wasn't until optical astronomer Martin Schmidt observed the optical spectrum of one of these objects, 3C273, one of the first quasars identified, that the true nature of these enigmatic sources began to emerge. Schmidt's findings revealed that this object's light had been redshifted to an extreme degree, indicating it lay billions of light-years from Earth. The implications were staggering. This meant quasars were not only far more distant than any other known objects, but were also emitting inconceivably vast amounts of energy. At the heart of every quasar lies a supermassive black hole, an object so dense that its gravitational pull warps the very fabric of spacetime around it. When a galaxy forms and its central black hole begins to pull in surrounding gas and matter, an accretion disk forms around it, heating up as particles are accelerated to immense speeds. This rapidly spinning disk releases extraordinary amounts of energy in the form of light, X-rays, and other radiation, creating what we observe as a quasar. The energy output of a quasar is nearly incomprehensible. In a single second, it can release more energy than our Sun will emit over its entire 10 billion-year lifespan. Quasars, therefore, mark the most extreme interactions between gravity, matter, and energy known to science. Understanding quasars has fundamentally reshaped our comprehension of galaxy evolution. Quasars are predominantly found in the early universe, meaning they provide glimpses into the cosmos' ancient past. By observing quasars, astronomers can study the formation and growth of galaxies over billions of years. We now believe that quasars are a phase in a galaxy's life cycle, typically associated with the early stages of galaxy formation. In the primordial universe, galaxies were chaotic, dense with gas and dust, and often merged with each other. These galactic collisions funneled gas toward the galaxy's centers, feeding the black holes within them and igniting quasars. As the black hole consumed this gas, the intense radiation it produced would eventually drive away any remaining gas, effectively halting further star formation and signaling the end of the quasar phase. Consequently, quasars provide insights not only into black hole activity but also into how galaxies themselves evolve, transition, and eventually mature. The study of quasars has also illuminated some of the fundamental processes that shape the universe's large-scale structure. Because quasars are so luminous, they act as cosmic lighthouses, allowing astronomers to probe the intergalactic medium, the gas and dust that exists between galaxies, across vast cosmic distances. As the light from a quasar travels through the universe, it interacts with clouds of gas, absorbing certain wavelengths and leaving a distinct fingerprint in the quasar's light spectrum. By analyzing these fingerprints, scientists can infer the composition, density, and temperature of intergalactic matter across different epochs. This has led to breakthroughs in understanding how the universe's matter has evolved, from the relatively homogeneous aftermath of the Big Bang to the complex web of galaxies and clusters we see today. In addition, quasars serve as natural laboratories for testing the laws of physics under extreme conditions. The immense gravitational forces and radiation around quasars push the limits of Einstein's theory of general relativity and quantum mechanics. For instance, quasars provide a unique environment where scientists can study how matter behaves as it approaches the event horizon of a black hole. The energy dynamics near a quasar's accretion disk are among the most extreme known to physics, enabling astronomers to investigate phenomena such as relativistic jets, where particles are ejected from the black hole's vicinity at speeds approaching that of light. These jets, believed to be the result of twisted magnetic fields, stretch across hundreds of thousands of light years and illuminate the vast distances between galaxies. By observing these jets, scientists gain insights into the behavior of matter and energy in regions where gravitational and electromagnetic forces reach levels unattainable anywhere else in the observable universe. Quasars are also central to unlocking mysteries about the so-called epoch of reionization, a period in the early universe when the first stars and galaxies formed and began to ionize the surrounding hydrogen gas. This era is crucial to understanding the transition from the dark ages of the universe, a time after the Big Bang when no stars had yet ignited, to a cosmos filled with light. Because quasars are among the most ancient objects we can observe, they offer direct evidence of the processes that ended the Dark Ages. Their light interacts with intervening hydrogen, allowing scientists to map the universe's evolution from a neutral, opaque state to the transparent cosmos we observe today. Furthermore, quasars have challenged and expanded our knowledge of cosmology in unexpected ways. The existence of quasars at such great distances implies they formed relatively soon after the Big Bang. This has raised questions about how supermassive black holes, the engines of quasars, could have grown so massive in such a short time. Traditional models of black hole growth suggest that it would take billions of years for black holes to accumulate enough mass to become quasars. The discovery of quasars only a few 100 million years after the Big Bang has thus forced astronomers to reconsider their models, prompting new theories on the rapid formation of black holes, such as direct collapse black holes or dense star clusters as early black hole seeds. As we delve deeper into the study of quasars, technological advancements continue to transform our understanding. Telescopes like the Hubble Space Telescope, the Atacama Large Millimeter Array, ALMA, and the upcoming James Webb Space Telescope have allowed astronomers to observe quasars with unprecedented detail, resolving features within the accretion disks and jets that were previously beyond reach. These observations have revealed complex structures, such as swirling gas clouds, magnetic fields, and even signs of winds and outflows that play crucial roles in regulating the growth of both the black hole and its host galaxy. As these technologies advance, the study of quasars will likely reveal even more about the universe's formative years, the interplay between black holes and galaxies, and the cosmic forces shaping our universe. Despite all we have learned, quasars remain an enduring mystery. The exact mechanisms governing the extreme energy outputs, the formation and sustenance of their colossal jets, and the precise impact of quasars on galaxy evolution are still subjects of intense research. Quasars stand as reminders of the universe's scale and power, illuminating both the limits of our knowledge and the boundless possibilities for discovery. These distant cosmic beacons guide us through the darkness of space and time, lighting our path as we strive to understand the origin and destiny of all matter in existence. Quasars serve not only as a cosmic phenomenon to observe but also as invaluable tools for probing the universe's vast and varied landscape. When we look at a quasar, we are peering across billions of light years, back to a time when the universe was young, chaotic, and rapidly evolving. The light from a quasar has traveled across epochs, bearing the imprints of every cluster of gas, every cloud of dust, and every cosmic event it has passed through. This ability of quasars to carry a record of the universe's history makes them irreplaceable to astronomers who seek to understand the origins and development of cosmic structures. One particularly fascinating aspect of quasars is their role in mapping the large-scale structure of the universe. By observing the light from numerous quasars distributed across the sky, astronomers can create a kind of three-dimensional map of the cosmos. As quasar light encounters different materials on its journey to Earth, it experiences tiny shifts in color and brightness, allowing scientists to deduce the nature of the intervening matter. In this way, quasars help us understand not only the distribution of galaxies, but also the web-like filaments of gas that stretch between them. This cosmic web of intergalactic gas is believed to be the scaffold upon which galaxies are built, tracing the invisible patterns of dark matter that govern the universe's architecture. Studying quasars has also opened a window into the physics of matter under extreme gravitational forces. Near the black hole that powers a quasar, matter is subjected to conditions that stretch our understanding of physics. The particles within the accretion disk are heated to millions of degrees, radiating energy across the entire electromagnetic spectrum. As these particles spiral inward toward the event horizon, they emit bursts of energy in unpredictable and often puzzling ways. Scientists are working to understand these emissions better, as they could reveal hidden aspects of black hole mechanics. Black holes are mysterious enough by themselves, with gravitational forces so strong that not even light can escape them. Adding the complexity of a quasar only deepens the mystery. For instance, scientists are still trying to fully understand how quasars create relativistic jets, beams of particles that shoot out from the poles of the accretion disk at nearly the speed of light. The jets produced by quasars extend for hundreds of thousands of light years, piercing through the galaxy and even beyond, into intergalactic space. The power source of these jets is still a topic of research, but they are thought to be driven by twisted magnetic fields near the black hole. These jets carry energy and material far from the central black hole, impacting the galaxy's evolution and even the surrounding environment. The energy carried by quasar jets can be so intense that it heats interstellar gas, sometimes halting star formation in a galaxy. This phenomenon, known as feedback, illustrates how black holes can have far-reaching influences on their host galaxies, essentially shaping the lives of stars and planetary systems. When a quasar's jets blow out significant amounts of gas, they remove the raw material needed for future star formation. In a sense, the quasar self-regulates its host galaxy, curbing the rate of new star formation and thereby marking a transition in the galaxy's life cycle. Quasars are also intriguing because of the sheer diversity of their appearances. Some quasars emit primarily in the optical range, while others are more luminous in X-rays or even radio waves. This diversity has led to classifications within the quasar family, with radio loud and radio quiet quasars marking different types. Radio loud quasars are those with powerful jets that emit strong radio waves, while radio quiet quasars, though equally energetic, lack such pronounced jets. This variability raises questions about the conditions that lead to such differences. Is it due to the orientation of the quasar relative to Earth? The properties of the black hole itself? Or perhaps the amount of material surrounding it? By studying these various types of quasars, astronomers hope to piece together a more unified theory of how these objects form, evolve, and interact with their environments. Another layer of mystery surrounding quasars is their role as cosmic timekeepers. Because quasars are incredibly distant, they act as markers of cosmic time, allowing scientists to study different eras of the universe's history. The light from a quasar that reaches Earth today left its source billions of years ago, providing a snapshot of the universe at that time. This look-back time is one of the most valuable aspects of studying quasars, as it provides direct observations of conditions that would otherwise be lost to the past. When we observe a quasar, we are not seeing it as it exists today but rather as it existed when the universe was much younger, possibly just a fraction of its current age. Each quasar, therefore, serves as a time capsule from the early universe, carrying with it insights into the formation of the first galaxies, the development of large-scale cosmic structures, and even the state of the intergalactic medium in that ancient epoch. In recent years, advances in technology have allowed astronomers to study quasars in greater detail than ever before. For example, the use of gravitational lensing has provided a novel way to observe quasars more closely. Gravitational lensing occurs when the gravity of a massive object, such as a galaxy cluster, bends the light from a distant object like a quasar, magnifying and sometimes splitting it into multiple images. This effect not only helps astronomers study quasars that would otherwise be too faint but also allows for detailed analyses of their structure and behavior. Gravitational lensing has even enabled scientists to observe quasars in different wavelengths simultaneously, providing a fuller picture of their energy output across the spectrum. Through these lensed quasars, researchers are gleaning insights into both the quasars themselves and the intervening matter bending their light. Beyond providing insights into the structure and evolution of the cosmos, quasars also present tantalizing evidence for the nature of dark matter and dark energy. These two elusive components make up the vast majority of the universe's content, yet they remain largely mysterious. The distribution and behavior of quasars could help astronomers understand how dark matter is distributed on cosmic scales, as well as how dark energy influences the expansion of the universe. Quasars act as tracers, marking out areas of dense matter and helping scientists map the invisible parts of the universe. By studying the large-scale distribution of quasars, scientists can test theories about dark matter clustering and the influence of dark energy over billions of years. Despite these breakthroughs, there are still profound questions surrounding quasars. One of the enduring puzzles is why quasars seem to have been far more common in the early universe than they are today. Observations suggest that quasars reached their peak activity several billion years ago, during a period often referred to as cosmic noon. After this era, quasar numbers declined sharply, and today we find them only in a handful of galaxies. This decline aligns with the fact that galaxies themselves are less active today, with fewer mergers and less gas to fuel supermassive black holes. It appears that as galaxies matured, the conditions that allowed quasars to form became increasingly rare. However, why precisely this change occurred, and what it implies for the fate of modern galaxies, is still an area of active investigation. The mystery of quasars touches on some of the most profound questions in cosmology and physics. Why do supermassive black holes exist in nearly every large galaxy? How do they grow, and why do some remain dormant while others become quasars? Could there be other types of luminous objects in the universe that we haven't yet discovered? And finally, could the study of quasars one day lead us to uncover new physics, revealing forces or particles that lie beyond the standard model? Each of these questions brings us closer to understanding not just quasars but the fabric of the universe itself. As we continue to push the boundaries of observation with more advanced telescopes and techniques, quasars will remain at the forefront of discovery. Their study has already rewritten our understanding of black holes, galaxy formation, and cosmic history. Yet quasars still hold many secrets, their light beckoning us from the distant past, challenging us to seek answers to questions we have only just begun to understand. The light emitted by quasars continues to offer profound insight into both their unique properties and the universe's broader narrative. As we delve deeper into the enigma of quasars, scientists are uncovering a story that weaves together extreme physics, cosmic evolution, and even the potential future of our universe. These brilliant cosmic objects offer a glimpse of what the universe looked like in its formative years, revealing information that extends our knowledge of everything from galactic formation to the cosmic phenomena shaping the farthest reaches of space. One of the most significant questions around quasars is how supermassive black holes, responsible for powering these dazzling objects, came to exist at such an early stage in the universe. Many quasars are found at extreme distances, meaning their light has traveled billions of years to reach us. This implies that they existed when the universe was only a fraction of its current age. But forming a black hole large enough to power a quasar would theoretically take much longer than the universe's age at that time. How, then, did these massive black holes grow so quickly in the early universe? This puzzle has led scientists to theorize that either black holes can grow at extraordinary rates under certain conditions or that the universe might hold clues to a previously unknown mechanism for rapidly forming these immense gravitational wells. One possibility to explain the rapid formation of these supermassive black holes is the concept of direct collapse. Instead of forming from a collapsed star, a process that limits the initial black hole size, some early black holes might have formed directly from massive clouds of gas that bypassed the star formation phase entirely. In this scenario, the gas would collapse directly under its own gravity, creating a black hole that begins life with a much larger mass. This process could, in theory, produce black holes in the range of thousands to millions of solar masses, providing the seed for a quasar's supermassive black hole. If direct collapse black holes did indeed form in the early universe, they could have acted as the nuclei around which the first quasars coalesced. Another idea gaining traction is that early galaxies experienced frequent collisions and mergers, creating turbulent environments rich in gas. These conditions could have fueled black holes at rates much higher than what we observe today, allowing them to rapidly gain mass. In the chaotic conditions of the young universe, gas was more abundant and densely concentrated, creating ample material for black holes to feed on. Frequent galaxy mergers also brought together multiple black holes, which could merge to form even larger ones. The combination of abundant gas and frequent mergers may have provided the perfect conditions for the growth of these early supermassive black holes, thereby giving rise to the luminous quasars we observe today. Quasars also play a significant role in exploring the structure of the early universe, especially during a period known as the Epoch of Reionization. Shortly after the Big Bang, the universe was filled with a hot, dense plasma. As the universe expanded and cooled, this plasma recombined into neutral hydrogen gas, plunging the cosmos into a dark age, where there were no stars or galaxies to light it. Eventually, the first stars and galaxies formed, and their radiation began to ionize the surrounding hydrogen, gradually turning it back into a state of plasma. This transition from a neutral to an ionized universe marks the epoch of reionization, a critical phase in cosmic history. Quasars, being some of the most luminous objects from this era, serve as natural beacons to study this transformation. When we observe distant quasars, we often find their light altered by the neutral hydrogen it passed through on its journey. This alteration, known as the Gunn-Peterson trough, is a characteristic absorption feature caused by intervening neutral hydrogen. By studying how this feature changes in quasars at different distances, astronomers can trace the progression of the reionization process. In essence, quasars offer a glimpse of a time when the universe was transitioning from darkness to light, showing us how the first galaxies and stars changed the environment around them. These insights are fundamental to our understanding of how light and matter evolved in the universe's earliest eras, as well as how the structure of the cosmos took shape. Quasars are not merely distant relics. They also impact their host galaxies and the larger cosmic web around them. When a supermassive black hole at the center of a galaxy transforms into a quasar, the tremendous amount of energy it releases doesn't just shine outward into space, it also affects the galaxy itself. This release of energy can heat, expel, or disrupt large amounts of gas in the host galaxy, essentially regulating star formation. In some cases, the energy from a quasar is so intense that it drives galactic winds, pushing gas and dust out of the galaxy. This process can effectively shut down star formation in the galaxy, leading to what scientists refer to as quasar feedback. Quasar feedback is thought to be one of the mechanisms that prevent galaxies from becoming too massive. Without this process, galaxies would continue to amass gas, forming new stars indefinitely. However, by expelling gas, quasars essentially control the rate of star formation, acting as a kind of thermostat for their galaxies. This self-regulating behavior provides clues about why galaxies today have the masses and structures they do. Quasar feedback might explain why some galaxies become red and dead, meaning they are dominated by older, red stars and have stopped forming new stars altogether. In a way, quasars might be seen as both creators and destroyers within their galaxies, fostering star formation through black hole growth, only to later limit it through feedback. Recent advancements in high-resolution imaging have allowed astronomers to observe the direct interaction between quasar jets and interstellar gas. Quasar jets, those powerful streams of particles launched at nearly the speed of light, are believed to be powered by the intense magnetic fields generated near the black hole. When these jets encounter gas within the galaxy, they can create shock waves that compress and heat the gas, triggering bursts of star formation in some cases. Alternatively, the jet can strip gas away from the galaxy, effectively starving it of the material needed to form stars. This delicate balance between nurturing and suppressing star formation highlights the complex relationship between a quasar and its host galaxy, suggesting that quasars play a crucial role in shaping the evolutionary path of galaxies. One of the most challenging aspects of quasar research is the vast distances involved, which often makes direct observation difficult. To overcome this, astronomers have turned to gravitational lensing, a technique that uses the gravity of a massive foreground object to magnify the light from a distant quasar. This phenomenon, predicted by Einstein's theory of general relativity, acts like a natural telescope, allowing scientists to observe quasars in greater detail. Gravitationally lensed quasars not only reveal details of the quasars themselves but also provide information about the intervening structures, such as galaxy clusters, that bend their light. In some cases, gravitational lensing has even allowed astronomers to observe quasars as they existed at different points in cosmic history, giving us a time-lapse view of their evolution. Gravitational lensing has provided extraordinary insights into the characteristics of quasar accretion disks and jets, regions that are otherwise too small to resolve with current telescopes. Through lensed observations, astronomers can detect slight variations in brightness and color across the quasar, unveiling details about the composition, temperature, and structure of the accretion disk. Such observations have confirmed that quasars have distinct inner and outer regions within their disks, with temperatures ranging from millions of degrees near the black hole to cooler regions further out. The data collected from these observations helps refine our understanding of black hole accretion, one of the least understood processes in astrophysics. In addition to being cosmic lighthouses and galactic sculptors, quasars may hold clues to the nature of dark matter and dark energy, two of the most elusive components in our understanding of the universe. Dark matter, though invisible, is thought to account for most of the universe's mass, while dark energy is believed to be driving the universe's accelerated expansion. By mapping the large-scale distribution of quasars, astronomers can trace the underlying skeleton of dark matter that shapes the cosmic web. Additionally, the study of distant quasars helps scientists measure the expansion rate of the universe, potentially shedding light on how dark energy has influenced the cosmos over time. As researchers continue to explore quasars, new questions arise that push the boundaries of astrophysics. Could quasars exhibit different characteristics depending on the properties of the black holes that power them? How do quasars evolve over time, and what ultimately leads them to fade and become dormant black holes? The answers to these questions could fundamentally reshape our understanding of galaxy evolution, black hole mechanics, and the fate of the universe itself. As we dig deeper into the mystery of quasars, we begin to see how these fascinating entities intersect with some of the most fundamental questions in cosmology and astrophysics. The intense brightness and incredible energy output of quasars make them invaluable tools for probing the universe's extreme conditions, both past and present. They serve as time capsules, preserving information about the universe when it was far younger, denser, and more chaotic than today. This cosmic illumination, generated by the relentless feeding of supermassive black holes, lights up the early universe, helping us map out its distant reaches. One of the enduring puzzles about quasars lies in their variability. Unlike stars, which emit light in a relatively steady manner, quasars can flicker and flare in brightness, sometimes dramatically, over periods ranging from days to months. This variability is thought to arise from fluctuations in the material surrounding the black hole, specifically within the accretion disk where gas and dust spiral inward. As this material experiences irregularities in density and temperature, it generates bursts of energy that ripple outward, making the quasar flicker like a cosmic lighthouse. Studying these changes in brightness allows astronomers to learn about the conditions within the accretion disk and the dynamic environment near the black hole. The study of quasar variability has opened a new dimension in understanding black holes and accretion disks. Observing these fluctuations has allowed scientists to measure the size of a quasar's accretion disk indirectly, even though these structures are far too small to resolve with telescopes directly. By analyzing the timing and amplitude of brightness changes, researchers can infer details about the disk structure and behavior. This information helps refine theoretical models of how material spirals into black holes and how this process generates the immense energy that powers quasars. Quasars also offer unique insights into the cosmic dark ages, a time after the Big Bang but before the universe was filled with light from the first stars and galaxies. During this period, the universe was primarily dark, and neutral hydrogen gas filled the cosmos. As quasars began to appear, their light pierced through this vast darkness, illuminating the hydrogen gas and marking the transition to a universe filled with galaxies and starlight. This illumination process is sometimes called cosmic dawn, and it represents a significant phase in the evolution of the universe. Quasars, therefore, are not just remarkable in their luminosity, they also played a role in lighting up the universe itself, helping end the cosmic dark ages and marking the birth of a structured, star-filled cosmos. Moreover, quasars can be used to study intervening matter between the quasar and Earth, allowing astronomers to map the distribution of gas, dust, and even galaxies along the line of sight. This mapping is possible because the light from distant quasars encounters various materials that absorb or alter it in specific ways. When the quasar's light passes through a cloud of gas, for example, certain wavelengths are absorbed, leaving an imprint in the light spectrum that reaches us. By analyzing these spectral fingerprints, scientists can determine the composition, density, and movement of intergalactic matter that would otherwise be invisible. Quasars, therefore, provide a unique tool for studying the cosmic web, the large-scale structure of the universe composed of interconnected galaxies, galaxy clusters, and vast regions of empty space. One of the intriguing phenomena associated with quasars is their potential role in forming massive galaxies. Some theories propose that supermassive black holes and quasars might not just be products of galaxy formation but active participants in it. When a young galaxy forms and its central black hole becomes active as a quasar, the intense radiation emitted could help shape the surrounding galaxy by regulating star formation and redistributing gas. This process could establish the observed relationship between the mass of a galaxy's central black hole and the overall mass of its stellar bulge, known as the black hole-galaxy bulge correlation. This correlation suggests a symbiotic relationship where the growth of the black hole and the growth of the galaxy are intimately linked. Quasar jets also play a part in shaping galaxy formation and evolution. These jets, composed of highly energetic particles launched from the vicinity of the black hole at nearly the speed of light, extend for thousands, or even millions of light years into space. When a quasar jet interacts with surrounding gas, it can trigger new waves of star formation or, conversely, expel gas from the galaxy, limiting the material available for future stars. This dual role, both fostering and inhibiting star formation, illustrates the complex influence quasars exert on their host galaxies and the intergalactic environment. The result is a feedback loop that helps regulate the growth and structure of galaxies across cosmic time. Another compelling aspect of quasar research involves gravitational waves, ripples in space-time caused by the acceleration of massive objects. When two supermassive black holes merge, they produce gravitational waves that can potentially be detected on Earth. Many quasars are located in galaxies undergoing mergers, where two black holes might eventually collide. Observing these systems could provide valuable insights into the process of black hole mergers and help scientists refine their techniques for detecting gravitational waves. As observational techniques improve, quasars and merging galaxies might one day serve as beacons for studying gravitational wave events across the universe. Furthermore, quasars may help unravel the mystery of dark matter. Though it does not emit light, dark matter exerts a gravitational influence that affects the motion and distribution of galaxies. By mapping the locations of quasars and analyzing their interactions with other galaxies, scientists can trace how dark matter shapes the cosmic web. Understanding how quasars are distributed across the universe provides indirect clues about the underlying structure of dark matter, offering a way to study this elusive component of the cosmos. With each new discovery, quasars continue to challenge our understanding and expand our knowledge of the universe. Their sheer brightness, incredible energy, and role in galaxy evolution make them a cornerstone of modern astrophysics. These cosmic beacons are more than just the brightest objects in the universe. They are keys to unlocking some of the most profound mysteries of existence, from the behavior of black holes to the nature of dark matter and dark energy. As we look to the future, With more powerful telescopes and advanced technology, the study of quasars promises to reveal even more about the universe's grand tapestry. The allure of quasars lies not only in their power and brightness but also in the way they represent both the known and the unknown. They are a bridge between the tangible and the mysterious, a reminder of the immense forces that govern the cosmos, and a testament to the ongoing journey of discovery that defines human curiosity. As we continue to observe and understand these incredible objects, quasars remain a vivid testament to the universe's capacity for extremes and complexity, driving us to explore deeper into the vast reaches of space and time. Quasars are indeed remarkable windows into the distant, early universe, offering astronomers the ability to observe epochs that are otherwise beyond our reach. As some of the oldest observable structures, they emerged during a period when galaxies and black holes were still forming, marking an era shortly after the universe's cosmic dawn. These ancient quasars are invaluable for tracing how the first massive structures came to be, revealing the building blocks of the cosmic framework we see today. The fact that quasars appear so bright despite their incredible distances is a testament to the sheer power of their energy sources. As we look deeper into space, we're also looking back in time. This time-traveling effect means that some of the quasars we observe today emitted their light when the universe was only a fraction of its current age, often less than 1 billion years old. Their intense luminosity allows them to cut through cosmic distances and interstellar material, reaching Earth as a faint glimmer from the primordial universe. Consequently, quasars act as fossils of light, capturing snapshots of the young cosmos and allowing scientists to study conditions that no longer exist. The discovery of these early quasars has challenged existing theories about how quickly supermassive black holes could have formed. To produce the brightness we observe, these quasars must have been powered by black holes billions of times the mass of the Sun. However, forming such massive black holes so soon after the Big Bang poses a significant puzzle. How did they grow so quickly? Traditional black hole growth models suggest that it would take much longer for a black hole to reach this size, even under the most favorable conditions. This challenge has led researchers to consider alternative scenarios, including direct collapse models, where massive black holes might have formed almost instantaneously from the collapse of vast gas clouds without first forming a star. These early, supermassive black holes could have formed within dense, young galaxies rich in gas and dust. In such environments, the collapse of large amounts of material directly into a black hole would be possible, allowing these objects to reach incredible masses very quickly. Another hypothesis suggests that mergers of smaller black holes or dense stellar remnants could accelerate the growth process. Observations of quasars, especially at very high redshifts, meaning from very distant times, continue to inform and test these theories, helping us refine our understanding of black hole formation and the conditions in the early universe. Quasars also serve as essential markers for mapping the expansion of the universe. Their extreme brightness allows astronomers to use them as reference points, helping measure how much space has stretched over billions of years. By studying the redshift of quasars, a measure of how much their light has been stretched to longer, redder wavelengths as it travels through expanding space, scientists can track the rate of cosmic expansion. This redshift measurement also provides clues about dark energy, the mysterious force driving the acceleration of the universe's expansion. Since quasars are visible across such vast distances, they enable researchers to study cosmic expansion at a scale that few other celestial objects can match. The study of quasars has also given rise to an entirely new field of research focused on quasar absorption lines. As the light from distant quasars travels to Earth, it passes through various clouds of gas and dust located along the line of sight. Each of these clouds absorbs specific wavelengths of light, leaving distinctive absorption lines in the quasar's spectrum. These absorption lines act like fingerprints, allowing astronomers to identify the chemical composition, density, and movement of gas in galaxies and intergalactic space that lie between the quasar and Earth. By analyzing these absorption lines, scientists can build a three-dimensional map of the universe's large-scale structure, including regions that are otherwise invisible. These absorption lines also reveal the history of star formation in the universe. When stars are born and die, They release various elements, such as carbon, oxygen, and iron, into the surrounding space. The presence and abundance of these elements in quasar absorption lines provide a record of past generations of stars. By studying quasars across different epochs, researchers can trace how the universe has been enriched with these elements over time, offering insights into the history of star formation and galactic evolution. An exciting new chapter in quasar research is unfolding with the development of advanced telescopes and instruments. Next-generation observatories like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are equipped with unprecedented sensitivity and resolution. These instruments allow astronomers to observe quasars in even greater detail and at higher redshifts, pushing our view of quasars further back in time. With JWST, for example, scientists can examine the environments around the first quasars, studying the structure of early galaxies and the conditions that led to the formation of the first supermassive black holes. The search for even earlier quasars is particularly important because it could reveal the conditions right at the edge of the observable universe. Discovering quasars from this period would allow astronomers to observe the universe's first few 100 million years, a time that has remained largely hidden due to limitations in telescope technology. If we can detect quasars from this epoch, it would not only mark a monumental observational feat, but also provide direct information about the first galaxies, stars, and black holes. Such observations could fundamentally change our understanding of the early universe and challenge existing cosmological models. Quasars have also played a role in advancing the field of gravitational lensing, where the gravitational field of a massive object, such as a galaxy, bends the light of a more distant object, like a quasar, behind it. This bending effect can produce multiple images of the same quasar, or even create arcs and rings. Quasars that appear behind massive galaxy clusters often exhibit these gravitational lensing effects, allowing astronomers to measure the mass of the lensing object and analyze the distribution of dark matter within it. This technique has helped scientists study not only the quasars themselves but also the properties of dark matter and the distribution of mass in the universe. In some cases, gravitational lensing can amplify the light from distant quasars, making them easier to detect and study. This amplification effect, known as gravitational magnification, provides a natural telescope for observing quasars that would otherwise be too faint. Lensed quasars are therefore crucial for expanding our view of the distant universe and studying quasars that reside at the very edges of observable space. The gravitational lensing of quasars continues to be a powerful tool in both cosmology and astrophysics, bridging the study of individual quasars with the broader structure of the universe. Quasars are also connected to one of the most mysterious and fundamental aspects of the universe, dark energy. Dark energy is thought to drive the accelerating expansion of the cosmos, and understanding its nature remains one of the most pressing questions in modern cosmology. Some researchers have proposed that by observing the distribution and properties of quasars over time, we might gain clues about how dark energy has influenced the universe's expansion history. This approach could help refine measurements of the universe's expansion rate and provide insights into the true nature of dark energy. In recent years, the study of quasars has also intersected with the search for high-energy phenomena, including cosmic rays and gamma-ray bursts. Some quasars emit powerful jets that produce high-energy particles capable of traveling vast distances through space. These jets, often observed at radio wavelengths, consist of particles accelerated to near-light speeds, and they can stretch across millions of light-years. When these jets interact with other material, they can generate shocks and magnetic fields, producing cosmic rays that eventually reach Earth. By studying quasars, scientists hope to understand the origins of these high-energy particles and how they travel across the universe. As we expand our understanding of quasars, we find that they are not merely isolated objects but rather fundamental components of the cosmic landscape. Their interactions with surrounding gas, galaxies, and intergalactic material illustrate the interconnectedness of the universe's structures and forces. Quasars, with their immense energy output and dramatic influence on their surroundings, underscore the power of black holes and the complexities of galaxy evolution. Each new discovery about quasars contributes to a broader picture of how galaxies form, evolve, and interact over billions of years. In many ways, quasars embody the extremes of the universe, showcasing both the unimaginable power of supermassive black holes and the delicate balance that governs cosmic structures. They are portals to the past, revealing details about the universe's infancy and the processes that shaped it. As we continue to push the boundaries of observational technology and theoretical modeling, quasars remain at the forefront of astrophysics, driving innovation and discovery in our quest to understand the cosmos. The journey to uncover the mysteries of quasars is ongoing, and each step brings us closer to answering fundamental questions about the nature of the universe. From their role in galaxy evolution to their contributions to our understanding of dark matter and dark energy, quasars stand as some of the most awe-inspiring and enigmatic objects in the cosmos. They remind us of the vast, largely uncharted universe that lies beyond our reach, beckoning us to explore, to question, and to marvel at the cosmic wonders that shape our existence. The exploration of quasars has revealed a tapestry of interconnected mysteries that stretch across the universe. These luminous beacons, with their incredible energy and staggering distances, serve as cosmic lighthouses, illuminating aspects of the cosmos that would otherwise remain hidden. Quasars aren't just powerful light sources. They are also indicators of extreme environments and forces at work, encapsulating the violent energy releases and intricate processes that govern the hearts of galaxies. Through their study, astronomers gain a more nuanced understanding of the mechanics driving not only quasars but also the galaxies and larger cosmic structures that surround them. The energetic jets emitted by quasars are another facet that has attracted significant scientific interest. These jets, which can stretch for millions of light years, are streams of particles accelerated to nearly the speed of light, spewing forth from the quasar's central black holes. While the mechanics of how these jets form remain partly shrouded in mystery, scientists understand that they are likely the result of magnetic fields around the black hole. As gas and dust spiral into the black hole's accretion disk, they generate intense magnetic fields, which then funnel particles along narrow paths. These jets blast away from the poles of the black hole, transporting energy and material across vast intergalactic distances. Observations of these jets reveal a fascinating paradox. Despite the enormous gravitational pull of a black hole, certain particles are somehow able to escape its grasp and travel outward with immense speed and energy. These jets have profound implications for the galaxies in which they reside, as well as the surrounding intergalactic space. When a quasar's jet collides with gas and dust in its host galaxy, it triggers complex interactions that can both promote and stifle star formation. In some cases, the energy from the jets heats up the surrounding gas to such an extent that it prevents the gas from cooling and condensing into new stars. This feedback effect can regulate star formation, effectively limiting how massive and bright a galaxy can become. In other cases, the jet's impact compresses nearby gas clouds, initiating bursts of star formation. This dual nature of quasar jets, both destructive and creative, highlights the complexity of galaxy evolution and the role quasars play in shaping the cosmic landscape. These feedback mechanisms connect quasars to a broader cosmological framework known as the cosmic web. The cosmic web is a large-scale structure composed of galaxies, gas filaments, and dark matter, all interconnected across the universe. Quasars, with their powerful jets and intense radiation, serve as key players in this network, influencing the gas that flows between galaxies. By studying quasars, scientists gain insights into how galaxies interact within the cosmic web, as well as how they exchange material over billions of light years. Understanding the influence of quasars on this vast structure helps clarify how galaxies evolve, merge, and disperse over cosmic time. The role of quasars in reionization, a period in the early universe when the first galaxies and stars ionized the surrounding hydrogen gas, adds yet another layer to their significance. After the Big Bang, the universe was initially filled with neutral hydrogen gas, which gradually cooled over hundreds of millions of years. When the first stars and galaxies ignited, they began emitting high-energy ultraviolet light that reionized the hydrogen gas, transforming the universe into a transparent state. Quasars, with their immense luminosity, played a critical role in this reionization process. Their powerful radiation helped ionize the intergalactic medium, contributing to the transition from a dark, opaque universe to one where light could freely travel. By studying distant quasars, astronomers can learn more about this epoch of reionization and the emergence of the first stars, galaxies, and black holes. These quasars from the early universe also offer glimpses into the chemical composition of young galaxies. As quasars' light passes through interstellar and intergalactic gas, it absorbs certain wavelengths, creating specific patterns in the quasar's spectrum. By analyzing these patterns, scientists can determine the abundance of elements like carbon, oxygen, and iron in distant galaxies. This analysis reveals the chemical history of the universe, showing how elements formed in the cores of stars were dispersed across galaxies. Observing quasars at different epochs enables scientists to trace the buildup of these elements over time, helping them understand the progression of star formation and supernova events that enrich the universe. The technological advancements in telescope design and data processing have opened a new frontier in quasar research. Instruments like the Sloan Digital Sky Survey (SDSS) have cataloged hundreds of thousands of quasars, allowing astronomers to analyze patterns and correlations across vast datasets. These large-scale surveys provide a statistical view of quasars, revealing trends in their luminosity, redshift, and distribution. By examining these patterns, scientists gain insight into the population dynamics of quasars, how they evolve, how their numbers change over time, and how they correlate with galaxy formation. In particular, SDSS data has helped establish the Quasar epoch, a period about 10 billion years ago when quasars were at their peak, shedding light on the cosmic conditions that fostered their development. Meanwhile, the upcoming Vera C. Rubin Observatory and the Euclid Space Telescope promise to take quasar studies to unprecedented levels. These observatories will conduct deep surveys of the sky, capturing faint quasars that have eluded detection until now. The Rubin Observatory, with its legacy survey of space and time, LSSD, will monitor the sky over a decade, allowing scientists to track changes in quasars over time. This capability is essential for understanding quasar variability, how their brightness fluctuates due to changes in their accretion disks or interactions with nearby objects. These observations will further refine models of quasar dynamics, offering more precise measurements of black hole masses, accretion rates, and the role of dark matter in quasar host galaxies. Quasars also offer a unique testing ground for general relativity and quantum mechanics, particularly in the regions closest to their central black holes. These black holes, with masses often reaching billions of times that of our Sun, create intense gravitational fields that warp space and time. By observing the behavior of matter in the vicinity of quasars, scientists can test theories of gravity under extreme conditions. The innermost regions of quasars, where spacetime is stretched and bent, provide valuable data for refining our understanding of black hole physics, potentially offering clues that bridge general relativity and quantum theory. The study of these extreme environments has implications not only for astrophysics but also for fundamental physics, helping researchers probe the boundaries of our current scientific paradigms. In addition to their scientific intrigue, quasars captivate the imagination. They stand as luminous sentinels in the darkness, embodying the universe's past and the mind-boggling power of black holes. They are reminders of the cosmos's untamed beauty and its violent nature, where creation and destruction are deeply intertwined. As we uncover more about these distant powerhouses, quasars continue to spark wonder, driving humanity's quest for knowledge and our desire to understand our place in the universe. The future of quasar research is bright, with each discovery offering deeper insights into the history of the cosmos and the forces that shape it. With ever-improving observational technology, theoretical models, and computational power, we stand on the cusp of unraveling more of their mysteries. These enigmatic objects, born in the early chapters of cosmic history, carry stories from the dawn of time, bridging the gap between the observable universe and the unknown. The journey to fully understand quasars is far from over, but each revelation brings us closer to piecing together the grand puzzle of existence. As scientists continue to study quasars, they reveal more about the fascinating interplay between energy, gravity, and matter in the universe. These luminous objects serve as some of the universe's oldest records, holding insights into the evolution of black holes, galaxies, and intergalactic space. Because quasars emit such high levels of light, they enable scientists to look back in time to an era when galaxies and black holes were first forming. This aspect of quasars, acting as windows into the past, makes them unique among cosmic phenomena. By examining them, we don't just see distant objects, we see ancient snapshots of the universe, allowing us to piece together a timeline of cosmic events that shaped everything from the formation of the first stars to the spread of dark matter across space. Quasars have also served as cosmic probes, giving astronomers tools to study the structure of the universe on the largest scales. The light emitted from quasars travels through vast regions of space, passing through clouds of gas and cosmic filaments, which are strands of gas and dark matter connecting galaxies and galaxy clusters across the cosmic web. When this light interacts with various particles, it leaves behind absorption lines in the quasar's spectrum, essentially creating a cosmic map. By analyzing these lines, scientists can gather information about the density, temperature, and chemical composition of matter across intergalactic space, giving a more comprehensive understanding of how galaxies and larger cosmic structures are distributed. One of the exciting discoveries made through quasars is the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars caused by clouds of hydrogen gas. Each line corresponds to a different gas cloud that the quasar's light has passed through on its way to Earth. This forest of lines provides a detailed picture of the structure of the universe over billions of light years, showing scientists how matter is distributed and how it evolves over time. Studying the Lyman alpha forest has revealed the presence of vast, web-like structures of hydrogen that form the backbone of the cosmic web. These filaments of gas eventually condense to form galaxies, meaning that by studying quasars, scientists can trace the stages of galaxy formation and evolution over the universe's history. In addition to mapping the large-scale structure of the universe, quasars have contributed to understanding dark energy, the mysterious force driving the accelerated expansion of the universe. By analyzing the distance and redshift of quasars, researchers can study how the expansion rate of the universe has changed over time. This method complements the study of supernovae, which has traditionally been used to measure cosmic expansion. However, because quasars are much more luminous and can be observed at greater distances, they allow astronomers to probe the expansion of the universe farther back in time. This approach holds potential for unraveling the nature of dark energy and determining whether its influence on the universe has remained constant or changed over billions of years. The observation of quasars also sheds light on the early formation of supermassive black holes. For a black hole to grow to billions of solar masses within a few 100 million years after the Big Bang, as seen in some quasars, it must have undergone periods of rapid accretion, consuming vast amounts of matter in a relatively short time. This discovery has led scientists to question the origins of these early supermassive black holes. Did they form from the collapse of massive stars? Or were there other mechanisms that could lead to the rapid buildup of such massive black holes? Various theories, including the idea that primordial black holes formed directly from the collapse of dense regions of gas in the early universe, are still under investigation, but quasars serve as key pieces of evidence in this ongoing mystery. Quasars have even been used to measure fundamental constants of physics. The light from distant quasars is so stable over time that it allows scientists to test whether certain physical constants, like the fine structure constant, have remained the same across cosmic time. The fine structure constant governs the strength of the electromagnetic force, which is essential for the structure of atoms and the stability of matter. By examining the absorption lines in quasar spectra, researchers can determine if there are any variations in this constant over billions of years. The stability or variability of these constants is crucial because any change could indicate new physics beyond our current understanding, possibly requiring revisions to the standard model of particle physics. Another area of active research involving quasars is gravitational lensing. When the light from a quasar passes near a massive object, like a galaxy or cluster of galaxies, the gravity of that object can bend the light, magnifying and distorting the quasar's image in a phenomenon called gravitational lensing. This effect sometimes causes the quasar to appear in multiple locations around the lensing object, creating a phenomenon known as an Einstein ring. Gravitational lensing not only allows astronomers to study quasars in more detail, but also provides an independent method for measuring the mass of galaxies and clusters that act as lenses. By analyzing how light is bent, scientists can deduce the distribution of both visible and dark matter in these intervening objects, giving a clearer picture of how mass is distributed on cosmic scales. Gravitational lensing also enables the study of quasars at unprecedented levels of detail. In some cases, the lensing effect can magnify certain features within a quasar, such as its accretion disk or jet, allowing astronomers to examine structures that would otherwise be too small or faint to observe directly. The magnification provided by gravitational lenses can reveal the dynamics within quasars, shedding light on the behavior of matter spiraling into black holes and the structure of jets emerging from their poles. This magnified view offers a window into the extreme environments around supermassive black holes and has allowed scientists to make discoveries about the conditions necessary for the formation of jets, accretion disk physics, and even the physical properties of black holes themselves. In addition to advancing cosmological research, quasars inspire new questions about the relationship between black holes and galaxy formation. In nearly every massive galaxy observed, there exists a central black hole, suggesting a close connection between black hole growth and galaxy evolution. Quasars, which represent an active phase of black hole growth, seem to coincide with significant changes in their host galaxies, such as intense star formation and the reshaping of galactic structure. These observations suggest that black holes and galaxies evolve in tandem, with black hole activity potentially regulating star formation rates and influencing the development of the galactic core. Understanding this relationship remains one of the central challenges in astrophysics, but quasars provide a unique vantage point for exploring these complex dynamics. In the quest to understand the origins of quasars, scientists have developed sophisticated computer simulations that model the early universe. These simulations recreate the initial conditions of galaxy formation and track the development of supermassive black holes over billions of years. By adjusting parameters and observing how quasars form and evolve in these simulations, astronomers can test theories about galaxy evolution, black hole growth, and the effects of cosmic feedback. These models are essential for interpreting observational data and for creating a theoretical framework that can explain the existence of such powerful objects in the young universe. With ongoing advancements in computing power, these simulations are becoming increasingly realistic, offering more detailed insights into the physics that govern quasars. The mysteries surrounding quasars continue to challenge and expand our understanding of the universe. They remain both sources of light and sources of profound questions, reminding us of the vast unknowns that still exist in our quest to comprehend the cosmos. As technology advances and our ability to observe and analyze the distant universe improves, quasars will likely remain at the forefront of discovery. These luminous objects not only illuminate the far reaches of space but also serve as beacons guiding us toward new scientific horizons, where answers to questions about gravity, matter, and the fabric of reality itself may one day be found. Quasars, with their brilliant luminosity and extreme energy outputs, continue to captivate astronomers not only because of their unique properties but also because of the profound cosmic questions they raise. These objects embody the awe-inspiring power of the universe, where even the laws of physics appear stretched to their limits, and they invite us to ponder some of the universe's most challenging mysteries. The energy output of a quasar is so immense that it often outshines its entire host galaxy, even when it's billions of light-years away. To put it in perspective, the energy from a single quasar can be 1,000 times greater than all the stars in the Milky Way combined. This incredible luminosity is largely due to the rapid consumption of matter by the supermassive black hole at the quasar's core. As matter spirals inwards, it forms an accretion disk around the black hole, where intense friction and gravitational forces heat the material to extreme temperatures, generating vast amounts of electromagnetic radiation that span the entire spectrum, from radio waves to gamma rays. Understanding how quasars sustain such high energy levels has revealed significant insights into black hole physics and accretion processes. The accretion disk surrounding a quasar's black hole is one of the hottest and most extreme environments in the universe. In these disks, gas and dust spiral inward at nearly the speed of light, creating conditions so extreme that traditional physics struggles to fully describe them. The accretion process is highly efficient, converting a significant portion of the mass energy of infalling material into radiation. This process is responsible for the extreme luminosity of quasars and allows them to shine brightly over vast cosmic distances. Yet this brilliance isn't just a spectacle, it's also a scientific tool. Because quasars are so bright and distant, they enable scientists to probe regions of space that would otherwise remain hidden. One of the most valuable aspects of quasars is their ability to illuminate intervening space, offering a kind of cosmic X-ray view of the structures and materials that lie between us and these distant objects. This light in the dark effect has led to profound discoveries, especially in the fields of cosmology and intergalactic medium studies. For instance, the phenomenon of redshift in quasars, where the wavelength of light stretches as the universe expands, provides a way to measure vast distances across space and back in time. The higher the redshift of a quasar, the farther away it is, which also means that its light originated when the universe was much younger. High redshift quasars, therefore, offer a unique glimpse into the early universe, giving astronomers an opportunity to study the universe during its formative years, mere billions of years after the Big Bang. This ability to look back in time allows scientists to study how galaxies formed and evolved and to observe cosmic phenomena that occurred in the universe's earliest epochs. One of the most groundbreaking aspects of quasar research is how it sheds light on the so-called cosmic dark ages, a period after the Big Bang when the universe was filled with a dense, opaque fog of hydrogen gas. During this time, light from the earliest stars and galaxies was absorbed by this gas, making it difficult to see what was happening across the cosmos. However, quasars serve as beacons that can penetrate this fog. When the light from distant quasars passes through the hydrogen gas, it leaves specific absorption signatures in their spectra, which can be used to study the nature of this intergalactic medium. This process of hydrogen becoming ionized, known as reionization, is one of the key phases in the universe's history, and quasars provide the best observational data to study it. By analyzing how quasars illuminate the dark matter and hydrogen around them, scientists can map out the progress of reionization and determine how and when the universe became transparent to light. Another fascinating aspect of quasars is their influence on their surroundings. The energy released by quasars is so intense that it can drive powerful outflows of gas, often in the form of winds or jets. These quasar winds can reach speeds of thousands of kilometers per second, strong enough to blow material out of their host galaxy and into intergalactic space. This phenomenon is referred to as quasar feedback, and it plays a critical role in galaxy evolution. By blowing gas out of a galaxy, a quasar can limit the amount of material available for star formation, effectively controlling the growth of its host galaxy. This feedback process is believed to be one of the main reasons why galaxies and their central black holes grow in tandem, with the activity of one affecting the development of the other. The idea that supermassive black holes can shape galaxies, sometimes even stopping star formation completely, is a profound realization that reshapes our understanding of how galaxies evolve. Quasar feedback is also linked to the chemical enrichment of the universe. When quasars drive outflows of gas, they carry with them heavy elements that were forged in the heart of stars. These elements, such as carbon, oxygen, and iron, are spread throughout intergalactic space, seeding future generations of galaxies and stars with the building blocks necessary for life. This process of chemical enrichment highlights the role of quasars as cosmic recyclers, dispersing elements that will eventually become part of new star systems, planets, and possibly even life itself. Without quasars and the feedback mechanisms they produce, the universe would be a very different place, perhaps lacking many of the complex materials that are essential for biological development. The jets produced by some quasars are another area of active research, especially in understanding how these streams of particles are launched and how they propagate across such immense distances. Quasar jets are composed of high-energy particles accelerated to nearly the speed of light, often extending far beyond the host galaxy. These jets interact with the surrounding environment, sometimes triggering the formation of new stars in neighboring gas clouds or, conversely, disrupting the formation of stars by heating the surrounding gas. The exact mechanisms behind jet formation remain a mystery, although it is generally believed that magnetic fields play a significant role. Studying these jets provides insight into the behavior of matter and energy in the most extreme conditions, offering clues to the fundamental physics that govern the universe. The presence of quasars in different types of galaxies also raises intriguing questions about their origins and life cycles. For example, quasars have been found in both elliptical and spiral galaxies, suggesting that they can arise in a variety of galactic environments. However, they are most commonly associated with merging galaxies, where two galaxies collide and merge into a single, larger system. These galaxy mergers are violent events that disrupt gas clouds, triggering bursts of star formation and funneling gas toward the central black hole, igniting the quasar. This relationship between galaxy mergers and quasar activity suggests that quasars are part of a larger process of galactic transformation, where the merging of galaxies fuels black hole growth and, in turn, influences the structure and fate of the newly formed galaxy. As we continue to push the limits of observation with telescopes like the James Webb Space Telescope, scientists are uncovering quasars that date back to less than 1 billion years after the Big Bang. These ancient quasars challenge current models of black hole growth, as their supermassive black holes would have needed to form and grow incredibly quickly in the early universe. This finding has sparked new debates among scientists, leading to the exploration of alternative theories about black hole formation, such as the possibility of seed black holes, created directly from dense regions of gas without the intermediary stage of star formation. These seeds could potentially grow into supermassive black holes much more rapidly than previously thought, helping to explain the existence of such massive quasars in the early universe. As astronomical techniques advance, so does the promise of discovering even more about these enigmatic objects. Future observatories, such as the Square Kilometre Array, SK, will expand our ability to study quasars across the electromagnetic spectrum, from radio to gamma rays. These telescopes will not only enhance our understanding of individual quasars but also allow for large-scale surveys of quasars across vast regions of space, revealing patterns and distributions that could provide clues about the fundamental structure and evolution of the cosmos. In essence, quasars stand as monuments to the power and mystery of the universe, reminding us of how much remains unknown and waiting to be discovered. Their extreme luminosity, deep-rooted connection to black holes, and impact on galaxy evolution make them invaluable subjects of study in the quest to understand the cosmos. Every piece of information we glean from quasars is like a clue in a grand cosmic puzzle, helping us answer some of humanity's most profound questions. How did the universe begin? How did galaxies and stars form? And what lies in the future for a universe filled with such incredible forces? Through the study of quasars, we are gaining insights not only into the distant past but also into the fundamental forces that shape the universe on every level, from the tiniest particles to the largest galactic structures. These brilliant beacons from the depths of space invite us to explore, to question, and to wonder. In doing so, they bring us closer to comprehending the vast and intricate universe of which we are a part. Quasars remain a powerful reminder of the scale and complexity of the universe, highlighting just how much there is left to explore and understand. Their brightness and distance from us make them fascinating subjects not only for scientists but for anyone captivated by the cosmos. As we dive deeper into the nature of quasars, we realize they reveal much more than initially meets the eye. They offer insights into cosmic evolution, the life cycle of galaxies, and the fundamental processes at play in the universe. One of the most awe-inspiring aspects of quasars is how they challenge our conceptions of time and distance. When we observe a quasar, we're not merely looking across billions of light years, we're looking back in time. The light from some of the most distant quasars has traveled for over 12 billion years to reach us, meaning we see them as they were in the universe's infancy. This time travel effect allows quasars to act as windows into the past, showing us what the cosmos looked like in its early stages. By studying these ancient objects, scientists can learn about the conditions that existed shortly after the Big Bang and how matter began to organize into the structures we see today. Moreover, quasars reveal information about cosmic reionization, the period when the universe transitioned from being opaque to being transparent. After the Big Bang, the universe was initially a hot, dense plasma, but as it expanded and cooled, it entered a period known as the Dark Ages, where light could not freely travel through space. During this time, the universe was filled with neutral hydrogen, which absorbed most forms of radiation. It wasn't until the first stars, galaxies, and quasars began emitting energy that the hydrogen was reionized, making space transparent to light. Quasars, with their intense ultraviolet radiation, played a key role in this process, essentially lighting up the cosmos and helping to reionize the surrounding hydrogen. This phase of reionization was crucial for shaping the modern universe and determining the structure of cosmic matter. Through observations of quasar spectra, astronomers can study the forest of hydrogen absorption lines known as the Lyman-alpha forest. This phenomenon occurs when light from a distant quasar passes through clouds of hydrogen gas on its way to Earth. Each cloud absorbs light at a specific wavelength, creating a series of dark absorption lines in the quasar's spectrum. By examining these lines, scientists can map the distribution of hydrogen gas in the early universe, offering insights into the formation and evolution of cosmic structures like galaxies and clusters. These absorption lines also reveal the chemical composition of the intergalactic medium and trace the enrichment of elements across the cosmos, contributing to our understanding of how matter and elements dispersed after the Big Bang. Quasars also provide clues about the mysterious dark matter and dark energy that dominate the universe. While dark matter and dark energy are invisible and interact weakly with normal matter, their effects can be inferred through their influence on quasars and the surrounding cosmic structures. For instance, the gravitational effects of dark matter can alter the light paths of distant quasars, a phenomenon known as gravitational lensing. When a massive galaxy or cluster sits between Earth and a quasar, its gravity bends the light from the quasar, sometimes creating multiple images or brightening the quasar's appearance. This effect allows astronomers to see the distribution of dark matter and gain insight into its role in shaping the cosmos. Quasars have also become essential tools for studying dark energy, the mysterious force driving the accelerated expansion of the universe. By observing quasars across various distances, scientists can measure changes in the universe's expansion rate over time. This, in turn, provides data on how dark energy has influenced the cosmos throughout its history. Understanding dark energy remains one of the greatest challenges in modern physics, and quasars serve as cosmic markers that help trace the universe's expansion and dark energy's impact. Another remarkable feature of quasars is their variability. Quasars can vary in brightness over time, sometimes fluctuating within days or even hours. This variability is due to changes in the accretion disk surrounding the supermassive black hole. As matter falls into the black hole, instabilities and fluctuations within the disk can cause rapid changes in light output. This variability offers valuable insights into the physics of accretion and helps scientists refine their models of how matter behaves in extreme gravitational fields. The ability of quasars to vary on short timescales has led to a better understanding of black hole accretion processes and has provided a way to estimate the sizes of accretion disks based on the time scales of variability. Quasar jets, which extend for thousands or even millions of light years, are another intriguing aspect of these cosmic powerhouses. These jets consist of streams of charged particles propelled at nearly the speed of light, often extending well beyond the host galaxy. The mechanisms that produce these jets are not fully understood, but they are thought to involve intense magnetic fields generated by the rotating black hole. Quasar jets interact with the surrounding environment, sometimes triggering the formation of new stars or heating the intergalactic medium. These interactions can have far-reaching effects, shaping the formation and evolution of structures across entire galactic clusters. Jets from quasars can also emit radiation across the electromagnetic spectrum, from radio waves to gamma rays. Observing these jets across different wavelengths allows scientists to study their composition, structure, and energy levels. Some jets are highly collimated, maintaining a narrow beam over vast distances, while others spread out and form large lobes. The jet's structure and behavior are influenced by the properties of the surrounding medium, which makes them valuable tools for probing the intergalactic environment and understanding the interaction between galaxies and their surroundings. In recent years, astronomers have discovered that some quasars experience red outbursts, a phenomenon where they emit significantly more red light than usual. These outbursts are believed to be linked to changes in the accretion disk, possibly caused by the rapid ingestion of a massive object, such as a star or gas cloud. These dramatic shifts in light emissions further demonstrate the complexity and dynamic nature of quasars and highlight the unpredictable behavior of matter under extreme gravitational forces. The life cycle of quasars remains a subject of active research. Quasars are typically most active in the early stages of a galaxy's life, often fueled by interactions and mergers with other galaxies that funnel gas toward the central black hole. As the quasar consumes surrounding material, it eventually exhausts its fuel supply, causing its brightness to fade. The quasar phase is thus a temporary but transformative period in a galaxy's evolution, marking a stage of intense activity before settling into a quieter state. Understanding this life cycle helps scientists piece together the broader story of galaxy evolution and the role that supermassive black holes play in shaping the cosmos. Today, advancements in technology have allowed astronomers to detect more quasars and study them in greater detail than ever before. Instruments like the Event Horizon Telescope, EHT, which captured the first image of a black hole's event horizon, provide unprecedented views of these distant objects and may soon shed light on the inner workings of quasars. Meanwhile, space-based telescopes like the James Webb Space Telescope are expected to detect quasars at even higher redshifts, offering a glimpse into the universe's earliest epochs. As we continue to study quasars, we stand on the cusp of uncovering more about these enigmatic objects and their place in the cosmic order. Quasars serve as a reminder that, while we have made incredible strides in understanding the universe, there is still much to learn. Their brilliance and mystery encourage us to push the boundaries of what we know and to pursue answers to questions that remain unsolved. The journey to understand quasars is, in many ways, a journey to understand ourselves and our place in the cosmos. Through these ancient beacons, we can see back to a time when the universe was young and chaotic, filled with intense energy and rapid change. In studying them, we are also studying the origins of galaxies, stars, planets, and ultimately, the conditions that made life possible. Each discovery brings us closer to a comprehensive picture of the universe's evolution, shedding light on the forces that govern everything from the smallest particles to the grandest structures. Quasars represent one of the most extraordinary phenomena in the cosmos. Their staggering luminosity, driven by supermassive black holes, provides a window into the early universe and helps answer questions about galaxy formation, black hole physics, and the very fabric of spacetime. These objects stand as symbols of the cosmos's power and mystery, challenging us to explore further and seek a deeper understanding of the universe. As we unravel the secrets of quasars, we unlock new perspectives on the universe's origins, the nature of matter and energy, and the forces that continue to shape the cosmos on both grand and minute scales. The story of quasars is a story of extremes. Their brightness, size, and distance push the limits of our understanding and reveal the sheer scale of cosmic phenomena. When we think about their luminosity, it's almost incomprehensible. A single quasar can outshine hundreds of billions of stars, releasing as much energy as an entire galaxy. This incredible brightness is one reason quasars were discovered relatively early in the study of distant celestial objects. However, their light alone cannot explain the true complexity behind these cosmic beacons. What lies behind the glow is the fascinating interplay of gravity, matter, and the profound depths of spacetime around a supermassive black hole. The sheer energy produced by quasars comes from their powerful engines, the supermassive black holes at their cores. These black holes, often billions of times more massive than our Sun, act as gravitational sinks, drawing in matter from their surroundings. As gas, dust, and other debris fall toward the black hole, they form an accretion disk, a swirling, blazing hot ring of material spinning at nearly the speed of light. This accretion disk reaches temperatures so high that it emits tremendous amounts of electromagnetic radiation, from radio waves to X-rays. As material accelerates and heats up, it can release jets of plasma that shoot out at nearly the speed of light, creating immense, visible structures that extend far beyond the host galaxy. Interestingly, the physics governing these accretion disks and jets remain partially understood. At the center of it all is the interplay of intense gravitational forces, magnetism, and relativistic effects predicted by Einstein's theory of general relativity. The environment around a quasar's black hole is so extreme that even tiny changes in its magnetic field can have massive consequences, affecting the stability and brightness of the quasar. This combination of forces creates a dynamic, sometimes unpredictable system that can oscillate, flare up, or suddenly dim, depending on the activity within the accretion disk. Scientists are continually working to simulate and understand these mechanisms, hoping to unlock the full picture of how quasars sustain their energy over cosmic timescales. Quasars are not only invaluable for their light, but also for their timing and role in the universe's history. These objects are rare in the present-day universe. Most of the quasars we observe existed billions of years ago, when the universe was younger. This scarcity is not due to the disappearance of black holes, but because the fuel supply necessary to power a quasar often depletes over time. Young galaxies, still filled with dust and gas, frequently have active quasars, as this material readily funnels into the black hole, feeding the immense energy output. Over billions of years, however, this material diminishes, and most galaxies evolve into quieter forms, leaving behind only a dormant black hole that no longer exhibits quasar-like luminosity. This temporal nature of quasars gives scientists a snapshot of a critical phase in the life cycle of galaxies. By observing distant quasars, we can glimpse how early galaxies formed, interacted, and evolved. In some cases, quasars may have even helped shape the galaxies they reside in, acting as agents of cosmic change. The intense radiation and winds emitted from a quasar can expel gas and dust from its host galaxy, a process known as quasar feedback. This feedback can quench star formation, essentially halting the birth of new stars in a galaxy, and may ultimately dictate the final size and shape of the galaxy. In this way, quasars are thought to influence the balance between galaxy growth and decline, serving as both creators and destroyers in their cosmic neighborhoods. This impact of quasars on their host galaxies has profound implications for the study of galaxy evolution. Scientists have observed that the most massive galaxies tend to host the most massive black holes, which suggests a close relationship between a galaxy's mass and the size of its central black hole. This correlation implies that galaxies and their black holes evolve together, each influencing the other's development. It's a cosmic dance in which the galaxy nurtures the growth of the black hole, which in turn regulates the formation of stars and the distribution of matter within the galaxy. Understanding this interplay could unlock deeper insights into how galaxies like our Milky Way formed and evolved over billions of years. One of the most fascinating aspects of quasars is the connection they create across vast distances in the universe. Due to the gravitational lensing effect, quasars often appear in multiple images or even in circular patterns, known as Einstein rings, around intervening galaxies. This effect occurs when a massive object, like a galaxy cluster, lies directly between Earth and the distant quasar. The gravity of the intervening object bends and magnifies the light from the quasar, allowing astronomers to observe it in unique detail. Through gravitational lensing, quasars have become natural laboratories for studying dark matter, the invisible substance that makes up about 27% of the universe's mass. Dark matter exerts gravitational effects on visible matter but does not interact with electromagnetic radiation, making it challenging to observe directly. However, by studying the way dark matter influences the light from quasars, astronomers can map the distribution and density of dark matter in the universe. These observations reveal that dark matter is not uniformly distributed but clumped into structures that serve as cosmic scaffolding around which galaxies and galaxy clusters form. Quasars, as distant and bright sources of light, help reveal this hidden structure of the universe, providing critical evidence for the role of dark matter in cosmic evolution. Quasars also contribute to the study of dark energy, the mysterious force responsible for the accelerated expansion of the universe. By observing the brightness and redshift of quasars across different distances, astronomers can trace the rate of expansion over billions of years. This information offers clues about how dark energy has influenced the universe over time and helps refine our models of cosmic expansion. Quasars have thus become instrumental in our efforts to understand dark energy and its impact on the fate of the universe. As technology advances, astronomers are developing new methods to observe quasars and unlock more of their secrets. Modern telescopes equipped with high-resolution imaging and spectroscopy can capture quasars in incredible detail, revealing features previously unseen. Additionally, the development of radio and X-ray observatories has allowed us to observe quasars in wavelengths beyond visible light, expanding our understanding of their properties and behaviors. Instruments like the Very Large Array, VLA, and the Chandra X-ray Observatory have made it possible to detect the structure of jets, study the dynamics of accretion disks, and analyze the interactions between quasars and their environments in ways that were once unimaginable. Space-based telescopes, like the James Webb Space Telescope, JWST, are expected to provide even more groundbreaking insights into quasars. JWST is designed to detect the faint infrared light from the earliest galaxies, allowing it to observe quasars from a period only a few 100 million years after the Big Bang. With its unmatched sensitivity, JWST will enable astronomers to peer deeper into the universe's history and study the earliest quasars that formed in the cosmic dawn. These observations could offer new perspectives on the formation of black holes, the evolution of galaxies, and the processes that led to the large-scale structure of the universe. In a similar vein, projects like the Square Kilometre Array, SKA, a massive radio telescope currently under construction, promise to revolutionize our understanding of quasars. SKA will be the largest and most sensitive radio telescope ever built, allowing scientists to detect faint radio emissions from quasars across vast cosmic distances. By mapping the distribution of quasars in the early universe, SKA will help create a three-dimensional picture of cosmic evolution, shedding light on how quasars influence the growth of large-scale cosmic structures. Ultimately, quasars embody the mysteries that drive our quest for knowledge about the cosmos. They remind us that, despite our technological advancements and scientific discoveries, the universe still holds secrets beyond our current comprehension. Each new discovery about quasars deepens our understanding of the cosmos, challenging us to continue exploring and to embrace the unknown. Quasars are both a testament to the universe's power and complexity, and a source of inspiration for those who seek to understand it. As we look to the future, the study of quasars promises to reveal even more about the nature of black holes, the life cycle of galaxies, and the forces that shape the cosmos. By continuing to study these extraordinary objects, we not only learn about the distant universe but also gain insights into the processes that have shaped our own galaxy and our place within it. The journey to understand quasars is far from over, and as our tools and techniques improve, we can look forward to a deeper understanding of these luminous beacons that light up the vast reaches of space. The allure of quasars extends beyond their sheer luminosity. They also play a vital role in our understanding of the fundamental laws of physics. Their extreme environments offer a unique laboratory to test theories of relativity and to explore the nature of matter under intense gravitational fields. The behavior of particles and radiation in the vicinity of a supermassive black hole challenges our current physical theories, pushing the boundaries of what we know about the universe. This quest for knowledge has sparked collaborations among physicists, astronomers, and cosmologists worldwide, fostering a rich scientific dialogue about the nature of reality itself. One of the fascinating aspects of quasars is their role in the timeline of the universe. Their existence reveals critical information about cosmic evolution, including the formation of the first stars and galaxies. By observing distant quasars, we can glimpse a time when the universe was only a fraction of its current age. These observations suggest that quasars were abundant in the early universe, acting as signposts that illuminate the conditions prevalent shortly after the Big Bang. As quasars grew, they provided the energy necessary for the reionization of the universe, a process that transformed the predominantly neutral hydrogen gas of the early universe into ionized plasma. This phase shift allowed light to travel freely across the cosmos, enabling the universe to become transparent for the first time. The relationship between quasars and the reionization of the universe is a subject of significant research. Observations indicate that quasars, with their intense energy output, contributed to heating and ionizing the surrounding gas, influencing the formation of galaxies and the distribution of matter in the early cosmos. By studying the spectral lines of distant quasars, astronomers can detect the signatures of this reionization process, gaining insights into the conditions that prevailed during one of the most critical epochs in the universe's history. This ongoing research not only deepens our understanding of quasars but also informs us about the broader cosmic narrative, linking the dots between the birth of stars, galaxy formation, and the evolution of large-scale structures in the universe. Furthermore, quasars are intrinsically connected to the fundamental question of black hole formation. The exact mechanisms that lead to the formation of supermassive black holes, which power quasars, remain a mystery. Current theories propose several pathways for their formation, including the merging of smaller black holes, the collapse of massive gas clouds, or the direct collapse of massive stars. Observing quasars across different epochs allows astronomers to test these models and refine our understanding of how black holes grow and evolve over time. Recent studies have suggested that some supermassive black holes may have formed relatively quickly after the Big Bang, growing to enormous sizes within the first billion years of the universe. These findings challenge traditional views of black hole formation and suggest that some quasars may represent a distinct population of early black holes that formed in the dense environments of the early universe. This raises intriguing questions about the conditions necessary for such rapid growth, and the implications for galaxy formation in those early cosmic epochs. In addition to their cosmic significance, quasars have practical applications in modern astronomy. Their light acts as a cosmic beacon, helping to probe the intervening material between us and these distant objects. The light from quasars is often affected by the gas and dust in the intergalactic medium, allowing scientists to study the composition and density of this matter. By analyzing the absorption lines in the spectra of quasars, astronomers can infer the presence of various elements and compounds, including hydrogen, helium, and heavier metals. This data reveals the chemical evolution of the universe and the processes that contribute to the formation of galaxies and stars. Quasars also help us understand the distribution of dark matter in the universe. The gravitational influence of dark matter affects the light from quasars as it travels through space. By studying the way that light bends around massive structures, like galaxy clusters, scientists can map the distribution of dark matter and better understand its role in cosmic evolution. This understanding is crucial for constructing accurate models of galaxy formation and the large-scale structure of the universe. Moreover, the observational capabilities of modern telescopes continue to enhance our understanding of quasars. For instance, the development of wide-field surveys and high-resolution imaging techniques has led to the discovery of numerous new quasars, allowing for extensive statistical studies of their properties. These surveys have also uncovered connections between quasars and other astronomical phenomena, such as gamma-ray bursts and gravitational waves. The cross-disciplinary nature of these discoveries demonstrates how the study of quasars informs a broader understanding of the universe, fostering collaborations across various fields of astrophysics. As we continue to explore the cosmos, the future of quasar research looks promising. The next generation of telescopes, like the European Extremely Large Telescope, ELT, and the Large Synoptic Survey Telescope, LSST, will significantly advance our ability to observe quasars and other celestial phenomena. With improved sensitivity and resolution, these instruments will enable astronomers to probe the environments of quasars more deeply, study their jets and outflows, and investigate their relationships with host galaxies in unprecedented detail. In addition to ground-based telescopes, space observatories such as the James Webb Space Telescope will provide new insights into the earliest quasars, potentially allowing us to witness the first generations of supermassive black holes as they form. Observing these ancient objects will offer invaluable information about the conditions in the early universe and the processes that led to the formation of the cosmic structures we see today. The search for quasars also highlights the importance of citizen science in astronomy. With the advent of online databases and crowdsourcing platforms, amateur astronomers and enthusiasts have become invaluable contributors to quasar research. Initiatives like the Zooniverse project allowed the public to assist in the identification and classification of quasars, contributing to large-scale surveys that would be impossible for professional astronomers to complete alone. This collaborative effort enhances our understanding of quasars and engages a wider audience in the wonders of the universe. Quasars are among the most fascinating objects in the universe, illuminating our understanding of cosmic evolution and the fundamental laws of physics. Their extreme luminosity, powered by supermassive black holes, provides insights into the formation and evolution of galaxies, the nature of dark matter and dark energy, and the processes that shape the universe. As our observational capabilities continue to improve and our understanding of these extraordinary objects deepens, quasars will undoubtedly remain at the forefront of astrophysical research. By continuing to study quasars, we not only enhance our understanding of the universe's past but also pave the way for future discoveries that could reshape our view of reality itself. As we gaze into the depths of space, quasars serve as beacons of knowledge, guiding us toward the ultimate questions about our existence and the cosmos we inhabit. Their mysteries invite us to explore, learn, and embrace the unknown, ensuring that the journey of discovery continues for generations to come. As we further investigate the enigmatic nature of quasars, it's important to consider their influence on our broader understanding of the universe. The existence of these brilliant objects helps us piece together the cosmic puzzle, offering clues about the nature of galaxies, dark matter, and the evolution of the universe itself. By studying quasars, astronomers can delve into the conditions of the early universe, as well as the processes that govern galaxy formation and growth. Quasars challenge us to think critically about the nature of light and distance in our universe. Because they are some of the most distant objects we can observe, quasars provide a unique perspective on the history of cosmic evolution. Their light can take billions of years to reach us, effectively allowing astronomers to look back in time. This perspective enables researchers to study how galaxies and their central black holes evolve over cosmic time. For instance, by examining a range of quasars at different distances, scientists can identify trends in their luminosity, spectral features, and host galaxy properties, thereby uncovering the mechanisms that drive the evolution of both quasars and their host galaxies. One fascinating discovery relates to the correlation between the mass of supermassive black holes and the properties of their host galaxies. Research has demonstrated that more massive black holes tend to be associated with more massive galaxies. This correlation raises intriguing questions about how black holes and galaxies co-evolve. Are supermassive black holes responsible for regulating the growth of their host galaxies through feedback mechanisms? Or do galaxies create conditions that facilitate black hole growth? Addressing these questions could significantly enhance our understanding of galaxy formation and the role of black holes in the evolution of the universe. The influence of quasars extends beyond their immediate vicinity. Their powerful jets and energetic outflows can impact their host galaxies and the intergalactic medium. These processes, referred to as feedback, play a crucial role in shaping the environment around quasars. The energy and momentum released by quasars can heat the surrounding gas, preventing it from cooling and forming new stars. This feedback mechanism can regulate star formation within the host galaxy, impacting its evolutionary path. Understanding these interactions is vital for developing comprehensive models of galaxy evolution, as it highlights the complex relationships between black holes, galaxies, and the larger cosmic environment. Additionally, quasars serve as important tools for studying the structure of the universe. The distribution of quasars provides valuable insights into the large-scale structure of the cosmos. By mapping the locations of quasars, astronomers can investigate the distribution of matter, including dark matter, across vast cosmic scales. This information helps to refine models of cosmic structure formation and evolution, ultimately enhancing our understanding of the universe's architecture. The study of quasars also intersects with the exploration of cosmic inflation, a theory that describes the rapid expansion of the universe shortly after the Big Bang. Observations of quasars can provide indirect evidence supporting inflationary models by revealing the distribution of large-scale structures in the universe. The alignment and clustering of quasars can hint at the conditions present during the early universe, offering a glimpse into the dynamics that shaped our cosmic landscape. In recent years, the advent of new observational technologies has revolutionized our ability to study quasars. The development of multi-wavelength astronomy, which encompasses observations across the electromagnetic spectrum, from radio waves to gamma rays, has allowed researchers to obtain a more comprehensive understanding of these powerful objects. Each wavelength reveals different aspects of quasar behavior, providing insights into their physical properties, jet dynamics, and interactions with surrounding matter. The upcoming advancements in observational technology, particularly with telescopes like the Vera C. Rubin Observatory and the planned NASA missions such as the Wide Field Infrared Survey Telescope, WFIR-ST, promise to enhance our understanding of quasars significantly. These instruments will enable researchers to conduct large-scale surveys, identifying new quasars and monitoring their variability over time. Such monitoring is crucial for understanding the physics of quasars, including the mechanisms that govern their luminosity changes and the nature of their outflows. The cultural and philosophical implications of quasars are equally significant. As we explore the depths of the universe, quasars invite us to reflect on our place in the cosmos. The knowledge gleaned from studying these celestial objects inspires wonder and curiosity, prompting us to ponder profound questions about the nature of existence and our role in the grand tapestry of the universe. Quasars challenge our understanding of time, space, and the very fabric of reality, pushing the boundaries of human knowledge and igniting our collective imagination. The interplay between science and philosophy becomes especially relevant when considering the implications of quasars on the nature of time and causality. As we observe distant quasars, we are not just seeing their light, we are witnessing events that occurred billions of years ago. This temporal perspective raises questions about the nature of time itself. How does our understanding of the universe shift when we consider that our observations reveal the past, rather than the present? This contemplation of time encourages us to explore deeper philosophical questions about the nature of reality, consciousness, and our understanding of existence. Quasars also play a vital role in educational outreach and inspiring the next generation of astronomers and scientists. Their dramatic stories of formation, evolution, and the cosmic processes at play captivate the imagination of students and the general public alike. Programs that engage young people in astronomy often highlight quasars as prime examples of the wonders of the universe, fostering curiosity and encouraging future scientific exploration. The fascination with quasars can ignite a lifelong interest in science, technology, engineering, and mathematics (STEM) fields, ultimately contributing to the advancement of knowledge and innovation in these disciplines. As we forge ahead in our quest to understand quasars, we must acknowledge the collaborative efforts that underpin this field of research. The scientific community thrives on collaboration, with astronomers, physicists, and researchers from diverse backgrounds coming together to share knowledge, data, and insights. International collaborations and partnerships have led to groundbreaking discoveries in the study of quasars, enriching our understanding of the cosmos. This spirit of collaboration fosters a sense of global unity in the pursuit of knowledge. Looking toward the future, the study of quasars will continue to evolve, driven by advancements in technology and our ever-growing understanding of the cosmos. As we develop new observational techniques and theoretical models, we can anticipate uncovering even more mysteries surrounding these luminous objects. The potential for groundbreaking discoveries remains vast, and as we push the boundaries of our knowledge, we must remain open to the unexpected and the unknown. Quasars stand as remarkable beacons in the vastness of the universe, illuminating our understanding of cosmic evolution, black hole formation, and the fundamental nature of reality. Their luminous power serves as a gateway to exploring the history of the universe, offering insights into the formation of galaxies and the evolution of cosmic structures. As we delve deeper into the mysteries of quasars, we not only expand our knowledge of the cosmos but also foster a sense of wonder and curiosity that inspires generations to come. Quasars remind us of the beauty and complexity of the universe, inviting us to explore, discover, and question the very fabric of reality itself. The journey into the cosmos is ongoing, and as we continue to unravel the mysteries of quasars, we are reminded that the universe holds secrets waiting to be discovered, challenging us to venture further into the unknown. As we continue to explore the vast and fascinating realm of quasars, it's essential to consider their significance within the context of cosmological models and theories. Quasars are not merely objects of scientific curiosity. They are pivotal players in our understanding of the universe's history and evolution. Their extreme brightness and unique properties allow astronomers to probe the very nature of the universe's structure and the forces that shape it. One of the most intriguing aspects of quasars is their role as cosmic lighthouses. Their immense luminosity enables them to be seen across vast distances, making them invaluable for studying the evolution of the universe over time. Quasars serve as beacons that illuminate the cosmic landscape, helping astronomers chart the distribution of galaxies, dark matter, and the large-scale structure of the universe. By analyzing the light from quasars, researchers can glean information about the intervening material between the quasar and Earth, such as gas clouds and dark matter distributions. The study of quasars also contributes to our understanding of cosmic expansion. Observations of distant quasars have provided key insights into the universe's rate of expansion, which is driven by dark energy. The light from quasars has been instrumental in measuring the distance to galaxies and refining our understanding of the Hubble constant, the rate at which the universe is expanding. As we gather more data on quasars and their distances, we can enhance our models of cosmic expansion and address lingering questions about the nature of dark energy. Quasars are also essential for investigating the formation of large-scale structures in the universe. The clustering of quasars and their correlation with galaxy clusters reveal the underlying gravitational forces that govern the universe's structure. By mapping the distribution of quasars, astronomers can better understand the formation of filaments and voids in the cosmic web, which is a vast network of galaxies and dark matter. This information enhances our understanding of how matter is distributed in the universe and provides insights into the processes that shaped its evolution. In addition to their role in cosmic structure and expansion, quasars provide a unique perspective on the processes that govern black hole growth. The mechanisms by which supermassive black holes accrete matter and gain mass remain a topic of intense research. Observations of quasars reveal that these black holes can grow rapidly through accretion, sometimes gaining mass at rates that challenge our understanding of how such growth occurs. Studying the properties of quasars and their host galaxies can shed light on the feedback mechanisms that influence black hole growth, providing a clearer picture of the interplay between black holes and their surrounding environments. The spectral characteristics of quasars also offer vital clues about their composition and the physical processes occurring within them. By analyzing the light emitted from quasars across different wavelengths, scientists can identify the presence of various elements, such as hydrogen, helium, and heavier metals. The abundance of these elements can inform us about the chemical evolution of the universe and the processes that occur in the environments surrounding supermassive black holes. The presence of broad emission lines in the spectra of quasars indicates high-velocity gas moving close to the black hole, providing insights into the dynamics of accretion disks and the conditions that lead to quasar activity. Quasars are not static entities. They exhibit variability in their brightness over time. This variability can occur on timescales ranging from days to years and is often attributed to changes in the accretion rate of material onto the supermassive black hole. Understanding the nature of quasar variability is crucial for deciphering the underlying physical mechanisms driving their luminosity changes. Ongoing monitoring of quasars using telescopes equipped with advanced technology allows astronomers to capture these variations and gain insights into the processes occurring in the vicinity of supermassive black holes. Moreover, quasars can also serve as valuable cosmological probes for studying the intergalactic medium, IGM. The light emitted by quasars passes through the IGM, allowing astronomers to study the distribution and properties of the gas that exists between galaxies. This research can provide insights into the history of star formation, the influence of galactic winds, and the conditions that shape the evolution of galaxies over time. The interaction between quasars and the IGM can reveal important information about the cooling and heating processes that govern the universe's evolution, enhancing our understanding of the life cycle of galaxies. The discovery of quasars has led to a significant paradigm shift in our understanding of the universe. Initially identified in the 1960s, quasars were a source of mystery and intrigue, prompting researchers to reevaluate existing theories about galaxy formation and evolution. The realization that these incredibly luminous objects were powered by supermassive black holes challenged long-held notions about the nature of galaxies and their central engines. This transformative discovery has catalyzed a wealth of research, leading to significant advancements in our understanding of the cosmos. One of the key breakthroughs in quasar research has been the realization that quasars are not isolated phenomena. Rather, they are connected to the broader framework of galaxy evolution. The study of quasars has revealed the intricate relationships between black holes, galaxies, and the intergalactic medium. This holistic view emphasizes the interconnectedness of cosmic structures and underscores the need for a comprehensive understanding of the universe's evolution. As we look to the future, the ongoing study of quasars holds immense promise for advancing our knowledge of the universe. The next generation of telescopes and observatories, equipped with cutting-edge technologies, will enable us to explore quasars in unprecedented detail. These advancements will likely lead to new discoveries and a deeper understanding of the physical processes that govern quasars and their impact on cosmic evolution. In summary, quasars are among the most luminous and energetic objects in the universe, providing invaluable insights into the nature of supermassive black holes, galaxy evolution, and the overall structure of the cosmos. Their study has transformed our understanding of the universe, revealing the complex relationships between black holes, galaxies, and the intergalactic medium. As we continue to unravel the mysteries of quasars, we embark on a journey of discovery that deepens our appreciation for the grandeur and complexity of the universe. Quasars serve as a testament to the wonders of the cosmos, inspiring future generations of scientists and explorers to seek answers to the profound questions that lie beyond the stars. As we delve deeper into the enigmatic world of quasars, it's essential to highlight some of the most significant discoveries and advancements that have shaped our understanding of these extraordinary objects. One of the pivotal moments in quasar research came with the realization that quasars are not just distant cosmic phenomena but rather integral components of the universe's evolution. The connection between quasars and galaxy formation has sparked extensive research, illuminating the processes that drive the growth of both supermassive black holes and their host galaxies. The discovery of the first quasar, 3C273, in 1963 was a watershed moment in astronomy. Initially perceived as a star, its immense luminosity and the redshift of its light revealed its true nature as a distant object powered by a supermassive black hole. This finding not only opened the floodgates for further discoveries of quasars but also posed fundamental questions about the structure and dynamics of the universe. The extraordinary brightness of quasars allows them to be observed across vast distances, enabling astronomers to study the early universe and understand the conditions that prevailed shortly after the Big Bang. The role of quasars in our understanding of the early universe is particularly fascinating. By examining the light from distant quasars, researchers can probe the cosmic epochs when galaxies were forming and evolving. The light emitted by quasars serves as a time capsule, revealing the state of the universe at various points in its history. For instance, observations of quasars from a time when the universe was only a few billion years old provide crucial insights into the processes that led to the formation of the first galaxies and black holes. As we investigate the light from these distant objects, we also encounter the phenomenon of cosmic reionization. This critical period in the universe's evolution saw the transformation of neutral hydrogen into ionized hydrogen, which significantly influenced the visibility of distant quasars. By studying the spectral signatures of quasars and their interactions with the intergalactic medium, astronomers can gain insights into the timing and mechanisms of reionization, enhancing our understanding of the universe's early epochs. The connection between quasars and the large-scale structure of the universe is another area of active research. Quasars can be used to trace the distribution of matter in the cosmos, helping to map the cosmic web that comprises galaxies and dark matter. By analyzing the clustering of quasars, scientists can investigate the gravitational influences that shape the universe's structure. This mapping provides a clearer picture of how galaxies are distributed and how they have evolved over cosmic time. Moreover, the interplay between quasars and their host galaxies is a key aspect of our understanding of galaxy formation and evolution. The processes that govern the accretion of material onto supermassive black holes influence the characteristics of the host galaxy. For instance, feedback mechanisms, where energy and momentum are transferred from the active black hole to the surrounding gas, can regulate star formation within the galaxy. This interaction suggests that the growth of supermassive black holes and their host galaxies is a complex, interconnected process that shapes the evolution of cosmic structures. In recent years, advancements in technology and observational techniques have revolutionized our understanding of quasars. The advent of high-resolution spectrographs and powerful telescopes has enabled astronomers to study quasars in unprecedented detail. Observations across various wavelengths, from radio to gamma rays, allow for a comprehensive analysis of quasar behavior and properties. The multi-wavelength approach reveals the complexities of the physical processes occurring in the vicinity of supermassive black holes, providing insights into their accretion mechanisms and the resulting emissions. Additionally, the use of large astronomical surveys has facilitated the discovery of thousands of new quasars, expanding the catalog of known objects and enriching our understanding of their diversity. The ongoing Sloan Digital Sky Survey (SDSS) and other large-scale surveys have yielded a wealth of data, enabling researchers to investigate the properties of quasars in various environments and contexts. This treasure trove of information enhances our understanding of the evolution of quasars and their role in cosmic history. As we continue to refine our understanding of quasars, the search for their counterparts in the early universe remains a priority. Identifying and studying the most distant quasars provides insights into the conditions that prevailed during the formative years of the universe. These observations help us piece together the puzzle of how galaxies and supermassive black holes evolved over time and how the universe transitioned from a hot, dense state to the rich structure we observe today. Quasars also play a crucial role in testing fundamental theories of physics. Their extreme environments provide a unique laboratory for investigating the laws of nature under conditions that cannot be replicated on Earth. For instance, studying the behavior of matter and radiation near supermassive black holes challenges our understanding of general relativity and quantum mechanics. Observations of quasar jets and the dynamics of their surrounding accretion disks can provide crucial data for refining our models of black hole physics and the fundamental forces that govern the universe. The excitement surrounding quasars extends beyond their scientific significance. They have captured the imagination of the public and inspired generations of astronomers and astrophysicists. The sheer scale and intensity of these cosmic phenomena evoke a sense of wonder about the universe and our place within it. Quasars serve as a reminder of the vastness of the cosmos and the mysteries that lie beyond our immediate understanding. In popular culture, quasars have found their way into various forms of media, serving as symbols of the unknown and the limits of human knowledge. They represent the quest for discovery and the relentless pursuit of understanding the universe's fundamental truths. As we look ahead to the future of quasar research, we are on the cusp of exciting developments. The upcoming generation of observatories, such as the James Webb Space Telescope, JWST, will allow us to observe quasars in greater detail than ever before. With its advanced capabilities, JWST will provide insights into the formation of the first quasars and their role in shaping the universe's early epochs. This next wave of exploration promises to unveil new mysteries and deepen our understanding of these cosmic giants. Quasars are remarkable cosmic phenomena that illuminate our understanding of the universe's evolution, the dynamics of black holes, and the interplay between galaxies and their environments. Their immense brightness and unique properties enable us to probe the early universe, explore the formation of cosmic structures, and investigate fundamental theories of physics. As we continue to unravel the mysteries surrounding quasars, we embark on a journey of discovery that not only enhances our knowledge of the cosmos but also inspires future generations to explore the wonders of the universe. The enduring allure of quasars lies not only in their scientific significance but also in their ability to captivate our imaginations and challenge our understanding of the cosmos. As we continue to explore these luminous beacons of the universe, we are reminded of the profound mysteries that lie beyond the stars, inviting us to seek answers and unravel the secrets of the universe. As we dive deeper into the multifaceted nature of quasars, it's important to explore the various types and classifications that astronomers have established. While all quasars are powered by supermassive black holes, they can exhibit a range of characteristics that reflect their environments, distances, and the nature of their host galaxies. One of the most significant classifications is the distinction between radio-loud and radio-quiet quasars. Radio-loud quasars are characterized by their strong emission of radio waves, often accompanied by the presence of powerful jets that extend far beyond their host galaxies. These jets are composed of highly energetic particles that are ejected at nearly the speed of light, creating immense structures in the intergalactic medium. The presence of these jets indicates that the supermassive black holes and radio-loud quasars are actively accreting material at a high rate and have significant magnetic fields that drive this ejection of material. The most famous examples of radio-loud quasars include 3C273 and 3C48, which have provided key insights into the dynamics of quasars. In contrast, radio-quiet quasars emit relatively little radio radiation, but they are still incredibly luminous in optical and X-ray wavelengths. The mechanisms driving the emissions in radio-quiet quasars can differ significantly from their radio-loud counterparts. These quasars often have more complex accretion processes, leading to the emission of different spectral lines and energy distributions. The distinction between these two categories has implications for understanding the mechanisms of black hole growth and the feedback processes between black holes and their host galaxies. Another fascinating aspect of quasars is their variability. Quasars are known to change in brightness over time, with fluctuations occurring on timescales ranging from days to years. This variability provides vital information about the size of the emitting regions around the black holes. For instance, if a quasar's brightness increases dramatically over a short period, this indicates that the region emitting light is relatively small. By studying the light curves of quasars, graphs of brightness over time, astronomers can infer details about the structure of the accretion disk, the mechanics of the jets, and the dynamics of the surrounding material. The phenomenon of gravitational lensing is another exciting aspect of quasars. When a massive object, such as a galaxy or a cluster of galaxies, lies between a quasar and an observer on Earth, it can bend the light from the quasar due to the curvature of spacetime predicted by Einstein's general theory of relativity. This effect can create multiple images of the same quasar or even distort its appearance. Gravitational lensing not only enhances our understanding of quasars but also serves as a tool for studying the mass distribution of the foreground galaxies, providing insights into dark matter and the large-scale structure of the universe. In addition to their intrinsic properties, quasars also serve as essential tools for probing the universe. For example, they can be used to measure the expansion of the universe. The light from quasars can be affected by the expansion of space, and by observing the redshift of quasars at various distances, astronomers can track how the universe has expanded over time. This method has contributed to the understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. Quasars also play a crucial role in the study of the intergalactic medium, IGM. As light from a quasar travels through space, it interacts with the gas and dust present in the universe, absorbing certain wavelengths of light and leaving specific signatures in the quasar's spectrum. By analyzing these absorption lines, astronomers can infer the composition, density, and temperature of the IGM, providing valuable information about the conditions present during different epochs in the universe's history. This interaction sheds light on the reionization epoch, when the universe transitioned from a neutral state to one filled with ionized hydrogen. The study of quasars has far-reaching implications beyond astronomy. Their extreme properties have sparked discussions about fundamental physics, particularly in the realms of general relativity and quantum mechanics. For instance, the behavior of matter and radiation in the intense gravitational fields near supermassive black holes provides a natural laboratory for testing the predictions of these theories. Observations of quasars can reveal insights into the limits of our understanding of physics, particularly under conditions that cannot be replicated in laboratory settings. In the quest to further understand quasars, the field of astrophysics has embraced advanced computational techniques. The simulations of quasar environments help researchers model the complex interactions occurring around supermassive black holes. These models can incorporate factors such as magnetic fields, accretion disk dynamics, and jet formation, providing a comprehensive view of the processes driving quasar behavior. By comparing simulation results with observational data, astronomers can refine their models and enhance their understanding of the underlying physical mechanisms. Moreover, the search for the most distant quasars continues to push the boundaries of our observational capabilities. Identifying quasars that formed shortly after the Big Bang allows scientists to probe the conditions of the early universe. As telescopes become more sophisticated, astronomers are discovering quasars that existed when the universe was less than 1 billion years old, providing a unique glimpse into the processes that shaped the first galaxies and black holes. These discoveries highlight the intricate relationship between quasars and the evolution of cosmic structures. One of the most intriguing discoveries in recent years has been the identification of quasars with extreme properties, known as extreme or hyperluminous quasars. These quasars emit light at unprecedented levels, challenging existing models of black hole growth. Understanding how these hyperluminous quasars form and evolve could provide crucial insights into the early universe and the conditions that fostered the growth of supermassive black holes. The existence of such objects raises questions about the limits of black hole growth and the mechanisms that drive accretion. Furthermore, the study of quasars is intricately linked to the field of cosmology. Their ability to illuminate the universe's evolution and the distribution of matter enhances our understanding of the cosmos on a grand scale. By linking quasars to large-scale structures and the cosmic web, researchers can piece together a more comprehensive picture of how galaxies formed and interacted over time. This knowledge is essential for constructing models of cosmic evolution and addressing fundamental questions about the universe's fate. As technology continues to advance, future missions and observatories will play a pivotal role in enhancing our understanding of quasars. Projects like the European Space Agency's Euclid mission aim to map the distribution of dark matter and dark energy in the universe. This mapping will include the identification of quasars, helping researchers further investigate their connections to cosmic evolution. Additionally, the upcoming Vera C. Rubin Observatory in Chile, with its large-scale surveys, is expected to provide a wealth of data on quasars and their environments, facilitating groundbreaking discoveries in the years to come. Public interest in quasars has also surged, fueled by popular science media and documentaries that highlight their extraordinary nature. Their extreme luminosity and role in shaping the universe captivate audiences and inspire curiosity about the cosmos. Quasars serve as a reminder of the grandeur and complexity of the universe, encouraging people to explore scientific inquiries and ponder the mysteries that lie beyond our planet. The future of quasar research is bright, with new discoveries on the horizon. As scientists continue to unlock the secrets of these luminous beacons, we can expect a deeper understanding of the universe's origins, structure, and evolution. Quasars not only illuminate the cosmos but also challenge our understanding of fundamental physics, pushing the boundaries of knowledge and inspiring generations of astronomers and astrophysicists. In essence, quasars represent the intersection of the known and the unknown. Their extraordinary brightness and unique properties invite us to explore the mysteries of the universe, revealing insights about the nature of black holes, the formation of galaxies, and the evolution of cosmic structures. As we continue to unravel the enigma of quasars, we embark on a journey of discovery that transcends the boundaries of human understanding, inviting us to ponder the cosmic tapestry woven across time and space. With each quasar observed, we gain not only knowledge but also a sense of wonder about the vast universe in which we reside. As we look to the stars and contemplate the mysteries that lie beyond, we are reminded of our place in the cosmos and the infinite possibilities that await discovery. Quasars are not merely celestial objects, they are cosmic messengers that illuminate our understanding of the universe and challenge us to seek answers to the most profound questions of existence. As we conclude this exploration of quasars, we are left with a profound appreciation for their significance in the grand narrative of the cosmos. The study of these luminous beacons is a testament to the power of human curiosity and the relentless pursuit of knowledge. Quasars continue to captivate our imagination and inspire future generations of scientists, reminding us that the universe is full of wonders waiting to be uncovered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.